Right now, 0.2%. That is the total fraction of our own planet that human instruments have ever directly measured. We have produced detailed topographic maps of the surface of Mars. We have launched probes past the edge of the solar system, yet the ground beneath your feet, the actual interior of this planet, remains almost entirely unknown to science. In the middle of one of the deadliest deserts on Earth, a machine the height of a 24-story building is drilling a hole deeper than Mount Everest is tall. China launched the Chang'e-1 project in May 2023, targeting a depth of 11,100 meters inside the Earth's crust. What their sensors are already detecting at that depth is making geologists uncomfortable, and it does not match the models. We will descend this hole together in stages. The machine, the history of the last nation that attempted this, what is being found, and what those findings mean for energy, earthquake, science, and the global balance of technological power underground. The descent begins now. Subscribe before the first revelation hits. By minute 10, you'll want the entire series. The common assumption is that deep drilling is oil prospecting with a larger budget. It is not. It is not. The physics operating below 5,000 meters do not exist anywhere on the surface of this planet. Rock that appears solid begins to flow. Water appears where no physical model allows water to exist. And the heat violates every textbook model produced before 1990. By the end of this investigation, you will know exactly what Soviet scientists found at the bottom of the Kola Superdeep Borehole that they were not permitted to publish for 6 years, and what China's sensors are already detecting at comparable depths in the Tarim Basin. Anyone who followed the space race through the 1960s and early 1970s knows the particular feeling of watching a nation aim a machine at the unreachable and hold its breath. This is that moment, aimed downward. We follow the story in 3 layers: the machine, the history, and the implications. The first layer begins immediately. The Chang'e-1 drilling rig broke ground in May 2023 in China's Xinjiang region, targeting a depth of 11,100 meters, and within its first kilometers of operation, the sensors detected temperature gradients that exceeded every geological model the engineering team had built for that basin. That is not a declaration of achievement. That is the discovery of a discrepancy. In science, discrepancies are the only territory where the genuinely new is ever found. The location was chosen with precision. The Taklamakan Desert, at the heart of the Tarim Basin in western China, is one of the most arid environments on Earth. Annual rainfall in some zones measures less than 10 millimeters, less than half an inch per year. No river crosses its center. No significant biological activity disturbs the sediment below its surface. The rock formations beneath the Taklamakan have remained essentially undisturbed for hundreds of millions of years, producing a geological record of exceptional clarity. Reading the strata there is like reading a manuscript that has been sealed in a vault since before the first vertebrate animal walked on land. Consider the scale of what this project is physically attempting. The Earth's radius is 6,371 kilometers. Chang'e-1 is targeting 11.1 kilometers. If the Earth were reduced to the size of an apple sitting in your hand, that borehole would not penetrate the skin. It would scratch the surface coating. That scratch is the sum total of humanity's direct physical knowledge of this planet's interior. The textbook model of the crust, the version taught in geology classrooms since the mid-20th century, describes it as hot, compressed, and essentially solid, stable within human lifetimes, inert, except along the active fault boundaries that generate earthquakes. The data from Chang'e-1's early drilling already complicates this picture in a specific way. Under sufficient pressure and temperature, rock does not behave as a rigid solid. It enters a state between solid and liquid, capable of slow deformation across geological timespans. The technical term is ductile deformation. Think of it the way you might think of cold glass. Hard enough to shatter under a sudden blow, but given sustained pressure across centuries, it yields, it flows. Stop and translate that into physical reality. The ground beneath every city, every building, every road on this planet sits above material that is, at depth, continuously deforming. The motion is imperceptible at human timescale, but the motion is real and continuous. And in the Tarim Basin, it is now, for the first time, being directly measured by an instrument that can reach it. The temperature readings at Shendita 1's site run approximately 30% above the global baseline for a continental basin of this geological classification. The team's published interpretation is cautious, likely elevated radiogenic heat production in the granite basement rock underlying the Tarim sediments. But the anomaly is substantial, and it raises a question the project cannot yet resolve: what is generating that excess heat? And what does it indicate about the structure of the lower crust below 8,000 meters? The rig itself deserves a moment of consideration. The drilling tower stands 24 stories tall in a desert where summer surface temperatures exceed 50 degrees Celsius, and the nearest significant city is hundreds of kilometers away. Maintaining a structure of this operational complexity in this environment, ceramic drill component supply chains, high-temperature cooling systems, deep data transmission infrastructure is itself an engineering story that receives almost no coverage outside specialized journals. The visible machine is only the beginning of what this project actually requires. That question about the anomalous heat has a historical precedent. The partial answer: unexpected, unsettling, and officially classified 4 years after it was obtained, came from a borehole drilled in a frozen Soviet peninsula more than 5 decades ago. In 1970, the Soviet Union began drilling on the Kola Peninsula in what is now northwestern Russia, approximately 16 kilometers from the Norwegian border. The stated purpose was scientific: to reach the lower crust, gather direct measurements, and test the prevailing geological models of the era against actual sample data from depth. The unstated purpose was functionally identical to China's today: demonstration of technological capability at the absolute frontier of what a modern industrial nation could achieve. The Kola Superdeep Borehole reached its final depth of 12,262 meters in 1989. 19 years after the first drill bit entered the ground, it remains the deepest artificial point ever created on this planet. At the bottom, the hole is 23 centimeters wide, the diameter of a dinner plate, and what the drill cores brought to the surface invalidated 3 assumptions that Soviet and Western geologists had treated as settled science since the 1950s. The first was water. At approximately 9 kilometers depth, in rock that every existing model said would be too compressed and too hot for any fluid to survive, the drill cores contained liquid water, not surface water that had slowly migrated downward over millions of years. Metamorphic water. Water molecules chemically locked inside the crystal lattice of the surrounding minerals for billions of years, and released under the specific combination of heat and pressure that exists only at that depth. The models said it could not be there. It was there. The Soviet scientific team was ordered not to publish the finding for 6 years. The second discovery was biological. At 6 kilometers depth, far below any layer where organic material was expected to survive in any recognizable form, the drill cores contained fossilized plankton, 24 distinct species, preserved inside silica capsules, approximately 2 billion years old, intact enough to identify under a standard optical microscope. Think about that for a moment. 2 billion years. Preserved. The third finding was mineralogical. Trace concentrations of gold, in quantities technically classified as ore grade, were detected at depths where gold deposits had no established geological mechanism to form. The explanatory models for this finding still involve significant scientific uncertainty. If the Kola borehole were laid horizontally, it would stretch from New York City to Philadelphia. That distance represents the deepest point any human instrument has ever physically reached inside the Earth, and it is less than 1/3 of the way to the boundary between the crust and the mantle. The irony is worth noting. The Kola team was not stopped by lack of ambition or funding. They were stopped by thermodynamics. Below 10,000 meters, the rock temperature reached levels that no drill bit of that era could sustain. Components engineered to operate 4 weeks were failing within hours. The rock was behaving like slow-moving hot plastic, deforming around the drill string, applying lateral pressure that no casing material of that generation could resist. The project was formally abandoned in 1992. The shaft was capped with a welded metal plate. It sits today in an overgrown lot in Russia's Murmansk region, unmarked and unremarked. What China learned from Kola's failure informed every engineering decision made on Shandita. The critical advance, the single development that makes this attempt viable where Kola ultimately was not, is the production of ceramic, composite drill heads capable of sustained operation above 200 degrees Celsius. That one materials science breakthrough is the reason this descent is happening at all. The physical conditions below 7,000 meters are not merely difficult, they are, in the precise technical sense, incompatible with standard materials science. Ambient temperature reaches 200 degrees Celsius, hot enough to melt solder, hot enough to vaporize the standard drilling fluids used to cool the bit in shallower wells. Pressure at that depth reaches 1,300 atmospheres. Consider what 1,300 atmospheres means in physical terms. It means 13,000 kilograms pressing on every single square centimeter of drill pipe. That is the weight of a fully loaded cement truck, concentrated onto a surface the size of a postage stamp. Repeated, without interruption, across every centimeter of every pipe in the drill string, a column of steel and ceramic descending more than 7 kilometers into the earth. Standard drill steel begins to plastically deform under these conditions. Shandita 1's ceramic composite drill head, the design classified until 2022, is specifically engineered to maintain dimensional stability at these temperatures and pressures. It represents approximately a decade of materials research that received almost no public attention before the project was announced. Here is where the story becomes something other than an engineering achievement. The Tarim Basin, sitting directly beneath the Taklamakan Desert, holds an estimated 17 billion tons of oil equivalent in deep geological reserves. These deposits are not accessible by conventional drilling. They sit at depths between 8,000 and 12,000 meters, in formations that have never been commercially reached. The same borehole that is mapping the lower crust for scientific purposes is simultaneously the most sophisticated prospecting instrument China has ever deployed for its most strategically urgent energy objective: reducing dependency on imported hydrocarbons. One machine, 2 missions, one of them publicly declared. There is a third mission that neither official announcement addresses directly. The data that Shandita 1's sensors are gathering on subsurface stress fractures along the Tarim Fault system is being transmitted to China's National Earthquake Early Warning Network. Surface seismometers measure the effects of tectonic stress, the vibrations that arrive after a fracture has already occurred. Instruments operating at 10,000 meters measure the stress itself inside the rock before any fracture takes place. That is not an incremental improvement in earthquake prediction. That is a categorical change in what the word prediction means in this context. What is being assembled in the Taklamakan Desert is simultaneously a scientific probe, an energy reconnaissance instrument, and a seismic intelligence platform operating in a region where China's 3 major fault systems converge within 1,500 kilometers of the drill site. But the most unsettling part is still ahead, because what Shandita 1 finds at maximum depth will either confirm or permanently dismantle the foundational model of how this planet generates its internal heat. The Earth generates approximately 47 terawatts of heat from its interior. Continuously, total global electricity consumption in 2023 was approximately 28. The planet is producing more energy as waste heat than humanity currently uses every hour of every day, without fuel, without combustion, without the intervention of weather or season. The obstacle has never been the energy itself. It has been physical access to the source. Iceland heats more than 90% of its buildings using geothermal energy, drawn from depths between 2,000 and 4,000 meters. The system works because Iceland sits directly on the mid-Atlantic ridge, where the crust is thin and the heat source is unusually close to the surface, a geological exception, not a replicable model. Shandita 1 is proof of concept for accessing geothermal energy at 3 times that depth, in a location with no volcanic activity and no natural shortcut. If the engineering holds at 11,100 meters in the Tarim Basin, it holds anywhere on the continental crust. The implications for landlocked, resource-dependent nations are not incremental. They are structural. The seismic application follows a parallel logic. China's 2008 Sichuan earthquake killed approximately 87,000 people and arrived with essentially no warning. Borehole seismometry at 10,000 meters reaches the depth where fault stress accumulates before it releases. The zone where the geological conversation happens before the rupture. It does not measure the earthquake. It reads the conditions that precede it. What is the broader competitive picture? The United States abandoned its deep continental drilling programs in the 1990s. Germany's KTB borehole stopped at 9,101 meters in 1994, citing the same thermal limitations that ended Kola. Russia sealed the Kola shaft in 2008. China is currently the only nation on Earth actively pursuing the 10,000-meter barrier with modern technology and sustained institutional commitment. The phrase "new space race" applied to this situation is not a metaphor. It is a factual description. One nation, alone, at the frontier, while every other major scientific power watches from the position of having stopped. 3 findings from Kola require resolution before this story closes: the water, the fossils, and the heat anomaly in the Tarim Basin. All 3 trace back to the same class of mechanism: metamorphic processes operating in the lower crust. When rock is subjected to extreme pressure and temperature over geological time, the minerals within it undergo chemical transformation. Hydrated silicate minerals, rocks that contain water molecules locked within their crystal lattice, release that water when surrounding conditions cross specific thermodynamic thresholds. This is metamorphic water. It does not originate at the surface and migrate downward. It originates inside the mineral itself, from a process that has been running since the rock first formed. The water that Kola found at 9 kilometers was not anomalous. It was evidence that the lower crust is more chemically active at depth than any surface measurement had indicated. The fossilized plankton require a separate explanation. The organisms were not alive. They were encapsulated in silica during the original deposition of the sediment layers, approximately 2 billion years ago. The depth and pressure preserve them against the degradation that destroys organic material near the surface. Their presence at 6 kilometers does not indicate life at depth. It indicates something more consequential, that the geological record at depth is more intact and more legible than any surface sample can ever be. Consider what that implies for every conclusion drawn about Earth's history from surface cores alone. The Tarim Basin heat anomaly most likely reflects elevated concentrations of radioactive isotopes in the basement. Granite, uranium, thorium, and potassium-40, all of which undergo continuous decay and release heat as a byproduct. If the granite underlying the Tarim Basin is unusually enriched in these isotopes, the excess heat is locally generated, not volcanic, not tectonic, but chemical. And if Shandita 1's core samples confirm this, it opens the possibility of mapping radiogenic heat concentrations globally, identifying geothermal reservoirs that currently appear in no existing energy survey. Every model of planetary formation, every estimate of Earth's remaining geological activity, every projection of geothermal energy potential is built on inferred data. Seismic wave propagation, gravitational field measurements, laboratory simulations of conditions that cannot be fully replicated at the surface. Shandita 1 will produce direct physical measurements from inside the lower crust for the first time since Kola. Kola's direct measurements invalidated 3 foundational assumptions. It would be unreasonable to expect this descent to validate everything that was built in its absence. The 0.2% figure from the opening of this investigation is not merely an embarrassing statistic. It is the precise boundary of human certainty about the planet we live on. Everything beyond it is inference. Every major discovery about the Earth's interior plate tectonics, the liquid outer core, subduction zones, the convection currents that move continents, was made by instruments that never physically touched what they were measuring. We have been reading this planet's autobiography through a locked door, using the behavior of sound waves and gravitational fields as our only alphabet. The words were always approximate. The decision to drill is not really about oil, or energy, or seismic data. It is about the specific discomfort of living on a planet you cannot see into. Every civilization that has ever existed built its cities, its calendars, its foundational myths on the surface of something it did not understand. We have only now, in this century, developed the tools to ask the question directly. Not mathematically, not symbolically, but physically, to push a machine into the ground and read what is actually there. Somewhere below the Taklamakan Desert, a ceramic drill bit, no wider than a dinner plate, is pressing through rock that has not moved in 300 million years. The sensors attached to it are transmitting temperature and pressure readings to engineers on the surface. The readings do not match the predictions. Te never do at this depth. We have always lived above the answer. We are finally asking. History keeps its biggest secrets in plain sight. Subscribe. We know where to look.